Right, everybody's PC on, okay? Let me jungle bite you first. Okay. Somebody's on. 21? No, nobody's at 21. You're not on. Okay. Don't have. What's happening? Oh, okay. Got there already. You see my screen? 809. Somebody is refusing to. Who is that? Oh, okay, all here. Right. I will return you your quiz after I've marked it. Next session I'll return it to you, okay? So it's over already, forget about it, let's move on. But I think the whole purpose is for you to at least spend some time catching up or revising on the material from chapters 1 to 6, right? And just a quick recap before we move on to what we're going to discuss today, chapter 7. Okay, if you recall from the first in the first three lectures, lectures 1, 2, and 3, or chapters 1, 2, and 3 of the course, the first three lectures were on MATLAB, and hopefully after the three lectures you have a really good idea of how to at least make use of some of the programming constructs in MATLAB, and also programming in MATLAB to solve problems in mathematics. And then in chapter 4 or lecture 4, we very quickly did a review of ordinary differential equations, the analytical solutions for both first order ODEs and second order ODEs. Then in lecture 5, we discussed initial value problems and numerical methods of solving initial value problems. So concepts or methods like the Euler method, improved Euler's method, RK4, and also we look at one approximation method called Picard's iteration to solve initial value problem. In lecture 6, we look at boundary value problem. And for boundary value problem, if we want to use simple and standard kind of numerical method, it would be finite difference method. Of course, there are other methods. So in fact, we look at one other method called the Rayleigh-Ritz method. That is a little bit complicated, but it gives us a sense that there are other methods that exist other than finite difference method. So there are pros and cons of these methods. And you'll find that something like finite difference method, very easy to implement, easy to understand and so on, but may not be as accurate as you would like it to be. Something like Rayleigh-Ritz method may be very powerful and very flexible and very accurate, but the implementation may not be so easy or straightforward. So in numerical methods, there's always this give and take. Whether you want efficiency or you want accuracy. Whether you want easy to implement or you want something that will give you very flexible kind of results. In life, it's like that. There's always a trade-off somewhere. So then we move on to what we're going to do today. From now on, we're going to look at partial derivatives and partial differential equations. So before we can understand partial differential equations, we have to basically look into the details, a lot of concepts within partial derivatives first. So today's lecture, we're just going to introduce partial derivatives, and then subsequently, the next few lectures we'll look at partial differential equations as well as numerical methods for partial differential equation. And that is actually the ultimate goal of this course. We want to reach a point where we can solve partial differential equations using some kind of numerical methods computational methods, and then also be able to analyze some of the solutions in terms of its accuracy, convergence, consistency, and so on. Okay, so let's look at partial derivatives. Now, why do we need partial derivatives, or even something like function of more than one variable? Very often you look at things that we have been able to try to represent or model using ordinary differential equations. Is the main problem with ordinary differential equations. It's very useful, can represent many things, but there's only one independent variable in an ODE, because that's the nature of ODE, only one independent variable, right? But in real life, many of the quantities or phenomenon that we are trying to represent very often depend on more than one independent variables. Okay, so these are some examples. We just take a very simple example of a volume of a cylinder. If you write down the volume of a cylinder, it depends on, or it has the formula will contain variables involving its height, and maybe its area of base, or the radius of the base, and so on. So there will be more than one variable. The temperature of a metal plate. You have a metal plate, so you measure its temperature. So there is a position where you measure it. So there is the position which is independent variable. And if you measure at a different point in time, the temperature may also change. So it also depends on time. So the temperature depends on two things now, at least, right? The output of a certain economy may also depend on the amount of labor and capital, and so on. So these, I give you a few examples from different fields already. So that's why we need to, in order to be able to represent more physical phenomenon or even systems in real life, we really need to consider the calculus of function of more than one variables. Okay, and that's the reason why we want to look at or study partial derivatives, because that directly links us to calculus of functions of more than one variable, of several variables. So let's examine this first illustration here, this example, where is a fairly, I would say, not too difficult, quite simple example. Suppose we have a metal bar. Okay, so we have this metal bar here. For simplicity, let's say this metal bar is 1 meter long. So at this end, x is equals to 0. At this end, x equals to, say, 1 meter. Okay, units is not so important here. And so this metal bar will have its temperature measured along its positions from x equals to 0 to x equals to 1. So at any point in time, if you point at this point, you put your probe at this point to measure its temperature there, you are fixing the position, right? You fix the position. So the position, for example, may be at x equals to 0.25. Okay. So at that point, if you measure its temperature could be some value. Okay, its temperature could be some value. Let's call it U1. So this U1 will be the temperature of let's say U at 0.25. That is my x, and maybe some value of t. Let's say 1 unit in t, and U2 maybe is U at 0.25 and 2 seconds at t equals to 2 seconds, and so on. So you find that already we know that if you fix at one point, fix a position, and you measure its temperature, it may vary depending on time. That's one way to look at it. Another way to look at it is to say, okay, I'm going to fix at a certain time. At time t equals to, say, 5. Okay, t equals to 5. Okay, and at time t is equals to 5, I'm going to measure the temperature at this point, at this point, at this point, at this point, and so on. So there will be various points here, right? So maybe at this point, this is u at 0, 5. Yeah, at this point, it will be u at, can you see? (0.1) and 5, and so on. So in other words, we see that in order to represent this temperature of this metal bar, we need to have an expression in terms of its position and the time where the measurement is taken. So if we use U to represent the temperature of the metal bar at any position x and at any time t, then we write U bracket xt. That is the dependent variable U in terms of the two independent variables x and t. And in this instance, maybe we have a kind of a formula to represent that particular temperature at some time. So you will find that in this formula, for example, you have a x there, you have a t there. These are the two variables. The rest are all just known constants or functions. And it is, say, for x between 0 and 1, and t bigger than 0. So we also call this like a semi-infinite kind of domain. Semi-infinite because it's bounded and at two sides by the x, but kind of bounded on one side only for t, but unbounded for t bigger than 0, right? It's upwards. So these are some examples. U at 0.25 t, then we can write down the function, but now because we have already fixed x to be 0.25, x equals to 0.25, we can get rid of the x there and then write a simpler function which is now of only one variable, or we can put down u at x20. That will be the distribution of the temperature, or the different values of the temperature along the x-axis, or along the positions, or I should say along the length of the metal bar at a fixed time t equals to 20. That would be this expression here, right? So we would say an expression like this will be we can describe it as the temperature, how the temperature changes at a particular point over time. Okay, that is the first one. The second one will be how is the heat or temperature distributed along the metal bar at a fixed time. Okay, that's how we would say it in terms of interpreting the expressions. Now, so now we look at something a little bit more abstract. We don't have a metal bar, we don't have something physical to sort of imagine. But suppose we just consider a function f defined in terms of two variables x and y. We write it as such: f(xy) equals to square root 1 minus x squared plus y squared, like this. And so it means that for every ordered pair xy inside the domain, okay, there will be a value, because you can put, let's say, x equals to some value, y equals to some value. Of course, it must be values that will give you a result when you take square root 1 minus x squared plus y squared, right? Then it should be given a unique real number, which is given by your f(xy). That means whatever that you evaluate is a unique real number. It cannot be Monday is one number for this pair of xy, Tuesday is another number for the same pair of xy. So it is unique, right? So for instance, if you put x equals to 0.4 and y equals to 0.6, of course you can work it out to be some number and so on. So that is what we will call a function of, in this case, two variables. All right, and let's look at an example to see how we can extend the idea of domain and range that you know from your understanding of function of one variable to something like this, which is a function of two variables. Okay, so look at example 1. You're asked to find the domain and range of this function, which is given as fxy equals to square root of x minus y. So let's see. Okay. Example 1, we have fxy equals square root x minus y. So we are asked to find the domain, meaning that the domain here will refer to all the set, the whole set of the ordered pairs xy that will give you a value, and in this case real function, so a real value fxy. I say that again. You want to find the set of ordered pairs xy. That's the domain. You want to find the set of ordered pairs xy that will give you a real value, acceptable real value for fxy. So what would be real values, possible real values for fxy? So we look at the expression square root x minus y. So long as x minus y is positive, you can find the square root. And if you can find the square root, it will be a real number, right? So which means that we need to find the ordered pair xy such that what? X minus y bigger than or equals to 0, right? So as long as this is bigger than 0, it also means that your fxy is defined. Okay, it means it has some definite value is defined. Okay, so it's quite obvious. This means that we need x bigger than or equals to y. That's all. So, but then we need to write it properly in terms of the domain, right? Therefore, the domain is, now it's a set, so let's write it as a set. It's a set of all the ordered pair xy, okay, such that x is bigger than or equals to y, where your x and y are both real numbers, right? This is how you write it, the domain. What about the range? What about the range? What do you think? Range, let's say it will be a value, wouldn't be ordered pair, it would be just a number, a value. The range will be the set of all the numbers z, or the values z, such that what?
All they are equals to 0.
Yes, okay. All the non-negative, right? Because it's under the square root. So all the non-negative values, real numbers. Non-negative real numbers. Okay, so if you are asked to let's look at it graphically, sketch the domain. Let's sketch the domain. Don't think it's hard. Should be able to do it. The domain will be in the xy plane, and we draw the line x equals to y, which is this line here, right? And it will be one side of the line. So which side is it? This side, right? So this is our domain. Now that we know roughly what is the meaning of function of, let's say, two variables, we know something about the range and domain. Sometimes it's useful to be able to visualize the the function itself. Essentially, if we want to graph something like this, a function f(x,y), function of two variables, will set, let's say, z equals to f(x,y), and it will then describe a surface in a three-dimensional space like this, for example. So this is the surface plot, if you like, of the f(x,y) equals to square root of 1 minus x squared plus y squared. Why is it that in this particular picture we only see what we call the upper hemisphere, or the hemisphere above the xy plane? Is because it's because we have a square root sign here, so it is taken to be only the positive values of z. All right, but we can also visualize such functions in a different way using what we call level curves or contour plots, contour lines. So if we say, for instance, maybe I just use this part of the paper. If we say, for instance, we had what we had was that f(x,y) is equals to square root 1 minus x squared plus y squared, right? And this is, we let this be equals to z, what do I say, not z, k, right? And we set different values of k, of course permissible values of k only. And then if we set this to k, and we can work out an expression involving x, y, and the constant value k. I say k, you set it to be, I don't know, some number, all right? And then you just work it out. You should be able to find an expression in x and y and k, and that will give you a curve on the xy plane. And that curve on the xy plane is known as your level curve, right? That will give you the level curve or the contour line. It is a line joining all the points with the same height in terms of the function value. So the same z value, in other words, right? So as what this point is saying, a level curve f(x,y,k) is a set of all points where the function takes the same value k. Okay, it's also where the graph has the same height, right? So if you have several of these contour lines on a plot, we call this a contour plot. We normally do not do this by hand. So for instance, if we look at example 2, the graph here is shown below, you see, down here. And this is sometimes what we also call the saddle function, right? The saddle function, because it looks like the saddle for that you put on the horse. Okay, so how do we do this? Well, if we don't do it by hand, normally we will use a tool. And you have just learned MATLAB, right? So you can use MATLAB. I'll demonstrate to you how this can be done. So this is a very simple set of instructions to construct the plot that you see in the notes. So again, we set your x, y, y. This is to set up the grid required or the mesh required for plotting your graph. So let's say we want the x to go from -4 to +4 in steps of 0.5. The y will also go from -4 to +4 in steps of 0.5. So lines 3 and 4 will help us generate those grid points, right? And then the next line 5 will help us generate the actual grid that we can use. So your x, y in square bracket equals to mesh grid using those two vectors that you have just defined in the x and the y directions. Then we use the next one, z equals to, this is just x squared minus y squared. But be careful, because x itself is a vector. If you want to square it, what you mean is to square the individual term, right? So you use what we call a element-wise operation, element-wise multiplication in this case. So element by element, that means the x1 multiplied by x1 minus y1 multiplied by y1. The next one, x1 x2 times x2 minus y2 times y2, and so on until you reach the end. Now, introduce to you some new commands here. Figure 1, figure 2. Okay, in the quiz you will ask what is the hold on for, right? Let's put on the same plot. If we want to see both the surface plot and the contour plot in two separate figures, you give a label to the figure. So you have figure 1 surface, figure 2 contour. So your lines 7 and 8 will then plot the surface plot onto figure 1. The identifier, that identifies the plot is 1, okay, figure 1. And then the contour will be on figure 2. So let's see what happens when we run this. If I were to click on this, you can see very quickly can you see figure 1 and figure 2? Okay, figure 1, you get the saddle like what we see, and figure 2 is your contour plots. You can of course control the density of the contour plot in the sense that you can control how many lines you want and so on, but I'm not going to go through that. I think that's too much detail already. So that's our example 2. We can very standard way of generating this kind of plots. All right, so this program, I believe, will be made available to you, should be available to you on Blackboard very soon after tonight, and you can try it out. Okay. So it will generate 2 plots like this. Okay. Let's move on. Okay, where is my slide? Sorry, he's not here. Okay. Right. So just a couple of notes here, a few notes here. In practice, we do not sketch these things by hand. Right, we use tools such as MATLAB or other graphing tools. If you know of other graphing tools, is fine. We can of course extend this idea of graphing and so on to functions of more than even 2 variables, but then it becomes difficult to see and describe what we actually want to plot once it goes beyond 2 variables. So for this course, generally, we will just focus on functions of 2 variables. Of course, again, the caveat is that if you want to extend, you can. It's just that it becomes too complicated. It's already may not be so nice to study anymore. We don't have time anyway. We have only 6 lectures left, including today. Right? Okay. The next concept before we take a break will be the idea of limit. Okay, I'm sure you have come across the formal definition of a limit for a function of 1 variable. At least for 1 variable, you will have come across, right? You know the epsilon delta definition, which everybody loves, right? Okay, I'm sure you have come across. But for function of more than 1 variable, let's say 2 variables, we'll concentrate on function of 2 variables. Let us just adopt a more working kind of a working definition rather than a formal definition in this particular case. Okay, so if we have a function f(xy), and if we let xy, okay, some point xy approach a certain point AB in the domain, okay, and if as it approaches, as xy approaches AB, the function value f(xy) approaches L, and if we are able to make f(xy) as close as possible to L by making the point xy as close as possible to AB but not touching AB, okay, then we say that the limit of fxy is L. Okay, you will find that whatever I just say, if you remove the y and you remove the b, it's just what you will understand for function of one variable fx, correct? So it's similar, but in symbols we will write it as limit of fxy as xy tends towards AB equals L. That's what we understand by the limit. Okay, we'll write it this way. So let's do a very quick kind of recap or on function of one variable, and then see if we can then move on, or not, I won't say translate, but extend it to function of two variables. So suppose this is my x-axis, and then I have a function maybe like this. This is function of one variable only, f of x, and suppose this is my point A. Now what we are saying is that if we say the limit of f of x is equals to L as x tends to A, if we say this, right, if we say the limit of fx as x tends to A is equals to L, what we are saying is that as we move nearer and nearer to A along x from both directions, like this and like this, the function value will go towards L. May not be as touching A. That means your x not equals to A, just approaching as close as possible. Okay, so you find that, well, this is one situation, right? This is one situation. Another situation could be like this. This is my x. This is my fxy, f of x. This is distract me. And this is my A. Now, at x equals to A, f of x is not defined, correct? There's a hole there. It's not defined. It's not continuous even at that point. Okay. However, we know that as we approach, so this is x. If we move along the x-axis from both directions, here and here, from negative and from positive, A, below A and above A, as we move closer and closer, you can see from the picture, the function value approaches here, approaches this point. In fact, it approaches this value L, let's say. Then, even if the function value does not exist, the function value at the point does not exist, the limit exists, right? So, the limit as x tends to A of f of x is still L in this case. Right? So in both these situations we are clear. Now let's look at another situation. So same thing, I have, this is my point A on the x-axis. Suppose now my function is like this. It's also not continuous. It comes from one side and then there is a hole here, but it's defined somewhere else and it continues, and this is my f of x. Okay? Okay? Clearly in this case, if you approach A from below, eventually you get very close, your function value takes this value L1. But if you approach A from above, right, your function value approaches this point and takes the value L2, right? They are not the same. Your left hand limit, yes, exists. Right hand limit also exists, but they are not the same. So the limit at that point does not exist. So in other words, we write down limit as x tends to A of f of x does not exist. This is what we understand from I'm just revising first year undergraduate calculus, right? Now, what about this one? Two variables. How do we extend this kind of concept to function of two variables? Well, in a function of two variables, you no longer can draw one line for your domain anymore. Right? You can't just draw an x-axis. What must you draw? You must draw the plane xy, correct? So we will consider the plane xy. And then we consider a point AB on the plane. So let's say the point AB is this point here. Okay, AB. Can you see? Yeah. Okay. So now what we are saying is this. You see the function, if you draw, I can't draw it, but if this is my x, this is my y, the surface plot maybe is somewhere up here, huh? Right? So at the AB there is a value there, but I'm not going to draw there. I'm going to just like draw its projection onto the plane, right? So you move towards AB. Now, you see, in this situation, we can say from the top, from the bottom, there are only two directions. Can you find any other direction if you have to stick onto on the domain? No, it's either from this only. But in this plane, how many directions are there? Infinitely many. There are too many. So basically, what we are saying is that in this situation, what we need to consider is all the paths possible, the infinite number of paths possible from everywhere that you can get inside the domain going towards AB. Okay, wherever it is going towards AB. And as you move closer and closer towards AB along any path, every path, all the possible paths, you still end up with the function value L, then the limit is L. So long as you have one path that doesn't end up in the same value L, the limit does not exist. It will be like this. Okay? So are we clear on the understanding of what is the limit of a function of two variables in comparison to a function of the limit of a function in one variable? So if you can understand this, it's just extending the same idea, except that now you don't have just two directions, you have all over. Okay, and so long as any one path has a different, gives you a different function values, if you move along the path, it gives you a different value as you go nearer and nearer to AB, right? It gives a different value from any one other path, then the limit does not exist. All paths towards AB must end up with the same function value. Then the limit exists. Okay, we will look at an example after we come back from a break. Okay, we take a 15-minute break.